For more than a century, physics has held firm on one idea. Nothing moves faster than light. Einstein's equations seem to draw a hard boundary around the universe, a cosmic speed limit that no engine, no signal, and no civilization could ever cross. This wasn't a technological restriction. It was structural, stitched into the very fabric of space and time. But hidden inside those same equations is something remarkable. Not a loophole that shatters the limit, something far stranger. A proposal suggesting that space-time itself could be stretched and compressed in just the right way, carrying a spacecraft across vast distances without technically breaking the speed of light at all. The catch? The conditions required are so extreme they make the original speed limit look almost trivial. And what scientists uncovered along the way reveals something profound about the deep architecture of reality. You cannot travel faster than light. At first, that sounds like a technological challenge, a hurdle waiting for a smarter engine or a better fuel. After all, humans once believed the sound barrier was impossible to cross. We believed heavier-than-air flight defied nature. History is full of limits that eventually fell, but the speed of light is different. It is not a wall standing in front of us. It is a property woven into the structure of the universe itself. To understand why, we have to go back to 1905, when a 26-year-old patent clerk named Albert Einstein quietly rewrote the rules of reality. Before Einstein, motion seemed straightforward. Throw a ball forward on a moving train, and its speed adds to the train's speed. Velocities stack like numbers in a sum. Common sense confirmed it. Everyday experience confirmed it. Newton's physics described it perfectly. But there was a problem hiding inside the equations of electromagnetism, equations developed by James Clerk Maxwell decades earlier. Those equations predicted that light travels at a constant speed, roughly 300,000 kilometers per second, regardless of how fast the source or the observer moves. That was strange. If you chase a car, it approaches you more slowly. If you run toward it, it comes faster. But light refused to behave that way. No matter how fast you ran toward a beam of light, it still approached at exactly the same speed. No matter how fast you ran away, it still caught up at that same rate. Experiments confirmed it. The speed of light did not add. It did not subtract. It simply stayed constant. Einstein made a radical proposal. Instead of changing Maxwell's equations, change our understanding of space and time. If the speed of light must remain the same for everyone, then space and time themselves must adjust to make that true. Distances must shrink. Time must slow. Simultaneity must become relative. This became the theory of special relativity, and it revealed something extraordinary. Space and time are not separate stages on which events unfold. They are woven together into a single four-dimensional fabric called spacetime. When you move quickly through space, you also move differently through time. Consider two twins. One stays on Earth. The other boards a spacecraft, travels at high speed, then returns home. According to relativity, the traveling twin ages more slowly. When they reunite, the spacefaring twin is younger. This is not science fiction. It has been measured. Atomic clocks flown on airplanes tick at a slightly different rate than clocks on the ground. Particles accelerated in laboratories live longer than they should, because time itself slows for them. As speed increases, this effect grows stronger. At 90% of the speed of light, time for the traveler slows to roughly half the rate experienced by someone at rest. At 99%, the effect becomes dramatic. Push closer still, and time nearly freezes relative to the outside world. But something else happens too. Energy requirements begin to explode. As an object accelerates, its kinetic energy increases. In relativity, energy and mass are intertwined through Einstein's famous equation, E equals mc squared. The more energy you pour into an object to push it faster, the harder it becomes to accelerate further. The relationship isn't linear. It curves upward steeply, like climbing a mountain whose slope becomes vertical near the summit. To reach exactly the speed of light would require infinite energy, not a large amount, not a colossal amount, infinite. And infinite energy does not exist. This is why the speed of light isn't merely difficult to reach. It is unreachable for anything with mass. Even if you converted entire stars into fuel, even if you harvested the energy output of entire galaxies, the mathematics still forbids crossing that boundary. The closer you get, the more the universe resists, as if the summit rises away from you with every step. But the deeper reason is even more unsettling. The speed limit is tied to causality, the ordering of cause and effect. In everyday life, we take for granted that causes come before effects. A spark ignites a flame, a stone strikes water, and ripples spread outward. This sequence feels absolute. Relativity shows that simultaneity is not absolute. Two events that appear to happen at the same time for one observer may occur in different orders for another observer moving at a different speed. Time is flexible, but there is still structure. Events connected by signals traveling at or below light speed maintain a consistent cause and effect order for all observers. If faster-than-light travel were possible, that structure collapses. In some reference frames, a signal sent faster than light would arrive before it was transmitted. With the right setup, you could receive a reply to a message you hadn't yet decided to send. You could intervene in the cause after already observing the effect. This creates logical paradoxes, loops in time where events undermine themselves. The speed of light prevents this. It preserves the sequence of history. Think of space-time as a vast architectural framework. The speed of light is not a decorative rule painted on its walls. It is a load-bearing beam running through the entire structure. Remove it, and the framework warps in dangerous ways. Relativity doesn't simply say you may not go faster. It says that going faster breaks the logic that holds reality together. This is why the barrier feels so absolute. Unlike earlier limits that humans overcame, this one is embedded in geometry itself. It arises from how space and time interlock. It protects the consistency of physical law across the universe. For decades, this seemed final. Nothing moves faster than light, not because we lack better engines, not because the right technology hasn't been discovered yet, but because the universe is built this way. And yet the story does not end there. Because in 1915, Einstein expanded his theory. He showed that space-time is not rigid. It bends and curves in the presence of mass and energy. And that insight would open a door no one expected. Objects cannot outrun light through space-time. But what if space-time itself could move? If special relativity built the wall, general relativity revealed the terrain behind it. In 1915, Einstein transformed physics again. This time not by redefining motion, but by redefining gravity. For centuries, gravity had been treated as a force, something invisible pulling objects together across empty space. Apples fell because Earth tugged on them. Planets orbited because the sun pulled them inward. Einstein proposed something far stranger. Gravity is not a force. It is geometry. Mass and energy bend space-time itself. Objects simply follow the curves. Imagine placing a heavy bowling ball on a stretched rubber sheet. The surface dips. Roll a marble across it, and the marble spirals inward. Not because the ball pulls it directly, but because the surface beneath it is curved. The marble is simply following the straightest possible path through distorted terrain. This is how planets orbit stars. This is how galaxies hold together. Even light, which has no mass, bends when passing near massive objects because space-time itself is curved. And here lies a subtle crack in the wall. Special relativity tells us nothing can move through space-time faster than light. But general relativity reveals something else entirely. Space-time itself is dynamic. It can stretch, it can compress, it can ripple like water disturbed by wind. We have actually measured those ripples. In 2015, scientists detected gravitational waves, distortions in space-time produced by colliding black holes. The universe itself vibrates. More dramatically still, the entire cosmos is expanding. In the early universe, during a period known as inflation, space expanded at an extraordinary rate. Regions once close together were driven apart faster than light could travel between them. This does not violate relativity. Nothing locally outran light. No particle sprinted ahead of the cosmic current. Instead, space itself expanded, carrying everything along. Think of dots drawn on the surface of an inflating balloon. The dots do not crawl across the surface. The surface stretches, and the distance between them grows. Two distant points can separate faster than any ant could crawl between them, not because the ant broke its speed limit, but because the balloon expanded beneath it. Today, the expansion continues. Distant galaxies recede from us at effective speeds greater than light, because the space between us stretches over vast scales. The speed limit applies to motion through space. It does not apply to the expansion of space itself. This distinction may seem technical, almost semantic, but it changes the landscape completely. If space can expand and contract, then distance is not fixed, it is elastic. And if distance is elastic, then perhaps travel is not only about motion, but about geometry. Imagine crossing an ocean. One option is to build a faster ship, fight the waves, burn more fuel, push harder against resistance. That is what conventional propulsion attempts in space-time. Push harder through a fixed distance. But what if you could shrink the ocean instead? What if the far shore could be drawn closer while the water behind you stretched away? The journey would shorten, not because you moved faster, but because the path itself changed. This is the conceptual leap that reshaped the conversation about faster-than-light travel. The cosmic speed limit says nothing outruns light within space-time. But general relativity suggests space-time itself is not rigid. It is a participant in the universe's dynamics. Einstein's field equations, which describe this geometry, do not forbid exotic shapes of space-time. They describe how mass and energy curve it, but they place no limit on how unusual those curves might be. For decades, physicists focused on solving these equations in one direction. Start with a distribution of matter, a star, a planet, and calculate the resulting curvature. That approach gave us black holes, expanding universes, gravitational waves. But mathematically, the equations work both ways. Instead of asking what curvature does this matter create, you can ask what matter would create this curvature. This reversal opens a door. What if we start with a desired geometry, a bubble of flat space-time moving across the universe, and then ask what kind of energy distribution would produce it? That question would remain largely unexplored until the late 20th century. But the foundation was laid the moment Einstein revealed that space-time is not static. It is dynamic architecture. In 1994, a theoretical physicist named Miguel Alcubierre did something deceptively simple. He stopped asking how to push a spacecraft faster and started asking how to move space-time instead. Rather than designing an engine, he designed a geometry. Using Einstein's field equations, Alcubierre proposed a solution describing a region of flat space-time, a calm pocket surrounded by a wave of distortion. In front of this region, space would contract. Behind it, space would expand. The flat interior would ride this distortion forward. The spacecraft inside would not accelerate. It would not feel thrust. It would not experience extreme time dilation or crushing forces. Locally, it would remain at rest. Yet from the outside, the entire bubble would move, potentially faster than light. To understand how radical this is, picture a sheet of fabric stretched tight. Now imagine creating a small ripple that travels across the surface. A coin resting on that ripple does not slide across the fabric. It simply rides the wave. The wave moves. The coin stays locally still. The warp bubble works in a similar way. The ship sits inside a pocket of undisturbed space-time. The distortion surrounding it propagates outward, carrying that pocket along. Nothing inside the bubble exceeds light speed relative to its immediate surroundings. The cosmic speed limit is obeyed everywhere locally. But the bubble itself can cross cosmic distances in a fraction of the time that light would need through normal, undistorted space. This is not a loophole in special relativity. It is an application of general relativity. Special relativity forbids motion through space-time faster than light. General relativity permits space-time itself to curve, stretch, and shift. Alcubierre's insight was to combine those two truths. The speed limit is preserved, but its meaning changes. Imagine two cities separated by 1,000 kilometers. Normally, you drive across the land between them. But suppose the land itself could fold like a page in a book, bringing the cities side by side. You would step across, the page would unfold, and you would arrive without ever moving faster than walking speed relative to the ground beneath your feet. The warp drive is that folded page. Not literal folding, but compression and expansion of space-time geometry. Ahead of the bubble, space-time contracts, reducing the distance to the destination. Behind it, space-time expands, increasing the distance from the origin. The result is translation without traditional motion. Mathematically, the Alcubierre metric describes a localized region of flat space-time embedded within a surrounding shell of intense curvature. The curvature profile determines the bubble's velocity. Increase the curvature gradient, and the effective speed increases. In principle, the equations allow arbitrary velocity, 10 times light speed, 100 times more. From Earth's perspective, a journey to a star 10 light-years away might take weeks. From the crew's perspective, time inside the bubble flows normally. No relativistic aging, no frozen clocks. It sounds almost like cheating. But the mathematics is exact. Alcubierre did not approximate the equations. He solved them. His metric satisfies Einstein's field equations precisely. That fact stunned the physics community. For decades, faster-than-light travel had been dismissed as a violation of relativity. And suddenly, relativity itself appeared to permit it, at least geometrically. The proposal ignited both excitement and caution, because while the equations answered one question, they raised many more. How would such a bubble be created? What kind of energy distribution would generate this curvature? Could the configuration remain stable? And perhaps most unsettling, what would this mean for causality? The first issue is conceptual. In general relativity, curvature arises from mass and energy. Stars bend spacetime. Planets bend spacetime. Even light contributes to curvature. So if you want a specific shape of spacetime, you must arrange mass and energy accordingly. Alcubierre's next step was to reverse engineer the solution. Given this desired bubble geometry, what arrangement of matter and energy would produce it? This is where the elegance of the idea met the harshness of physics. The warp bubble requires regions of negative energy density. Not simply less energy than usual, less than empty space itself. To understand why, recall what the bubble demands. Space ahead must contract. Space behind must expand. The geometry requires space-time to defocus in certain regions and focus in others. Ordinary matter always curves space-time in one direction, inward. It pulls, it focuses. That is why gravity attracts. To create the outward pushing curvature needed in parts of the bubble, the equations demand something exotic, energy that gravitates repulsively. In quantum physics, small negative energy effects do exist. The Casimir effect demonstrates that vacuum fluctuations between two closely spaced plates can produce a tiny region of negative energy density. But these effects are minuscule and fleeting. The warp bubble requires immense amounts of sustained negative energy. Early calculations suggested the total energy required would be equivalent to the mass of the observable universe. Later refinements reduced this estimate dramatically, to stellar masses, then planetary masses, and in some speculative analyses, perhaps even smaller. But even the most optimistic scenarios remain far beyond anything achievable. It is not merely an engineering challenge. It is a question of whether such energy can even exist in the required configuration at all. And that is only the first barrier. There is another complication hidden in the geometry itself: horizons. A warp bubble moving faster than light creates a boundary separating its interior from the external universe. Signals from inside cannot reach the front edge of the bubble. Why? Because the front boundary moves away faster than light relative to the interior. The crew cannot communicate with the region of space-time they are approaching. They cannot steer by sending instructions to the bubble's leading edge. Once formed and accelerated, the bubble becomes causally isolated from the space ahead. No course corrections, no braking signals, no steering adjustments. The geometry that enables superluminal motion also prevents control. And then there is the issue of arrival. As the bubble moves, it interacts with particles and radiation in interstellar space. Some models suggest these particles accumulate at the front boundary, compressed by the contracting space. Upon arrival and bubble collapse, that energy could release in a burst, potentially devastating whatever lies ahead. Other models suggest radiation buildup near the bubble boundary could destabilize it. Quantum effects at the horizon might produce intense particle creation, similar to Hawking radiation near black holes. The deeper physicists examined the proposal, the more complex it became. The warp drive is not forbidden by Einstein's equations. But Einstein's equations are not the whole story. General relativity is a classical theory. It does not include quantum mechanics. When quantum effects are considered, new constraints emerge. Quantum inequalities restrict how much negative energy can exist and for how long. Stability analyses reveal that the delicate curvature of the bubble may amplify tiny fluctuations catastrophically. The warp bubble is mathematically valid, but physically fragile. And yet, despite these immense challenges, the idea remains one of the most profound insights to emerge from theoretical physics in the late 20th century, because it revealed something extraordinary. The cosmic speed limit is not a simple prohibition. It is a layered defense. Locally, nothing outruns light. Globally, space-time can shift. But every attempt to harness that flexibility encounters deeper principles. Energy conditions, quantum constraints, causality preservation. The Alcubierre metric did not give humanity a starship. It gave us a mirror. It showed that the structure of reality is richer and more constrained than either optimism or pessimism alone could predict. The mathematics opened the door. The universe stood behind it, reminding us that permission on paper does not guarantee permission in practice. When Miguel Alcubierre finished writing down his warp bubble solution, the excitement lasted only until the next calculation began. Einstein's equations do not just describe geometry. They tie geometry directly to energy and matter. Every dip in the fabric must be paid for. So Alcubierre asked the unavoidable question: what kind of energy distribution would actually create this moving bubble of space-time? The answer was not merely inconvenient. It was shocking. The warp bubble requires negative energy density, not low energy, not zero energy, energy less than nothing, less than the vacuum of empty space itself. To understand why this matters, think of gravity as a curvature that pulls inward. Ordinary matter, everything from dust to stars, produces this inward curvature. It focuses paths. It draws trajectories together. That is why gravity attracts rather than repels. But the warp bubble demands something different. In front of the bubble, space must contract sharply. Behind it, space must expand. The geometry requires space-time to curve outward in certain regions, to defocus rather than focus. Ordinary matter cannot do this. Its curvature always pulls inward. The equations insist that only something with negative energy density could produce the required outward-pushing gravitational effect. And negative energy is not something we find waiting to be used. Quantum theory allows tiny glimpses of it. The Casimir effect, where two closely spaced metal plates alter vacuum fluctuations, creates a minuscule region where energy density dips slightly below that of empty space. But these effects are microscopic, fleeting, and incredibly small. The original warp drive calculation suggested the energy required might equal the mass energy of an entire star. Later refinements reduced the estimate, perhaps to the mass of a planet, or even less under certain geometric optimizations. But even a single kilogram of stable negative energy would represent something utterly beyond known physics. Worse still, quantum field theory imposes strict rules called quantum inequalities. These rules say negative energy cannot accumulate freely. If it appears, it must be balanced by positive energy nearby. And the more negative energy you try to concentrate, the shorter the time it is allowed to exist. It is as if the universe permits you to borrow against the vacuum, but only briefly, only in tiny amounts, and always with interest. The warp bubble demands a sustained, macroscopic region of negative energy arranged with exquisite precision. Nature does not appear willing to provide it. But suppose, just for a moment, that somehow we solve this. Suppose future physics unlocked stable negative energy in usable quantities. Would the warp drive then be possible? The deeper scientists looked, the more they realized the answer was not so simple. Even if negative energy existed in abundance, the warp bubble introduces another severe constraint: horizons. When a warp bubble moves faster than light relative to surrounding space, it creates a boundary, a causal horizon, similar in some ways to the event horizon of a black hole. Signals from inside the bubble cannot reach the front edge. The front boundary moves away from the interior faster than light. Any signal emitted from the spacecraft toward the bubble's leading edge can never catch up. This creates a profound problem. The crew cannot steer. They cannot send instructions to adjust the bubble's shape. They cannot slow it down by communicating with its boundary. They are sealed inside a region of space-time, cut off from the geometry that propels them. The very feature that enables faster-than-light motion, causal separation, also makes navigation impossible. It is like boarding a train that, once launched, cannot be stopped or redirected from the inside. The problem of stopping is equally troubling. To collapse the bubble safely at a destination, some mechanism must alter the space-time curvature ahead of the ship. But from inside the bubble, that region is unreachable by any signal. One speculative idea suggests the bubble would need to be managed from the outside, perhaps by infrastructure waiting at the destination. But that merely relocates the impossibility. Who builds that infrastructure? How is coordination achieved if communication cannot outrun light? Each solution leads to new complications. And then comes the issue of stability. The warp bubble geometry is delicate. It requires extreme curvature gradients at its boundary, regions that resemble, in some mathematical respects, the edges of black holes. Quantum field theory predicts that strong curvature can trigger particle creation from the vacuum, a phenomenon related to Hawking radiation. Calculations suggest that intense radiation could accumulate near the bubble boundary. This radiation might destabilize the bubble, draining energy or even destroying the configuration entirely. The very act of shaping space-time so dramatically could ignite quantum effects powerful enough to tear it apart. And even if stability were somehow maintained, there is the question of interaction with interstellar matter. Space is not empty. Even in the vast gulfs between stars, particles drift. Atoms, dust grains, cosmic rays. A warp bubble traveling through this medium would encounter them. Some models suggest they would accumulate at the front boundary, compressed by the contracting space ahead. Over a long journey, the energy buildup could become enormous. Upon arrival and bubble collapse, that accumulated energy might release in a burst of radiation intense enough to devastate a planetary system. In other words, even a successful journey could end catastrophically. Every layer of analysis reveals another constraint. Negative energy may not exist in sufficient quantity. If it does, control may be impossible. If control is solved, stability becomes uncertain. If stability is managed, radiation and matter interactions pose lethal risks. And threading through all of this is the deepest concern of all: causality. Faster-than-light travel between distant points allows the construction of closed time-like curves, paths through space-time that loop back on themselves. In certain reference frames, a superluminal round trip could allow arrival before departure. This is not a philosophical inconvenience. It is a logical fracture. If causes can follow effects, the predictive structure of physics collapses. Some theorists propose that quantum gravity, a theory not yet fully formulated, may contain mechanisms that prevent such paradoxes from ever forming. This idea is sometimes called chronology protection. If true, any warp bubble that threatened causality might destabilize automatically, destroyed by quantum effects before paradox could arise. The universe would protect its own consistency. The pattern that emerges is unmistakable. The warp drive is mathematically allowed. But each time physicists try to turn that mathematical permission into physical reality, deeper layers of constraint appear. It is like excavating through rock, only to find another layer of bedrock beneath. The speed of light is not defended by a single barrier. It is defended by an interlocking system of principles: energy conditions, quantum stability, causal structure, geometric consistency. Each principle reinforces the others. Remove one, and another stands in its place. For years, the exotic matter problem seemed like the single fatal flaw in the warp drive idea. If negative energy is required, and negative energy cannot exist in sufficient quantity, then the concept collapses. So physicists asked a different question. What if the problem isn't the geometry, but the type of energy we assumed was necessary? What if it could be done with only positive energy, the ordinary kind that fills the universe? At first glance, this sounds like a breakthrough. Remove the main obstacle, and perhaps the rest becomes manageable. But as always, the deeper you go into the equations, the more subtle the story becomes. Some of these new solutions describe what are known as subluminal warp configurations. They produce localized distortions in space-time that resemble a warp bubble, contraction in one region, expansion in another. But the overall motion remains below the speed of light. In these cases, the energy conditions of general relativity can be satisfied without invoking negative energy. The mathematics holds together cleanly. The geometry is elegant. But there is a crucial distinction. A subluminal warp bubble does not sever causal connection with the outside world. Signals can still pass between interior and exterior. The bubble can be influenced and controlled. It behaves more like a moving gravitational wave than a faster-than-light vessel. And because it remains below light speed, it does not bypass the fundamental barrier that special relativity imposes. It may allow novel propulsion methods, but it does not deliver superluminal travel. Other proposals go further. They attempt to design constant velocity warp geometries that mathematically allow superluminal motion using only positive energy distributions. The headlines can be dramatic, but there is a critical catch. Many of these solutions cannot be created from normal space-time. They describe configurations that must already exist, eternal geometries that cannot be switched on or off. They cannot accelerate. They cannot decelerate. They cannot be constructed from a flat region of space using known physical processes. It is like discovering a perfectly smooth tunnel connecting two distant mountains. But realizing the tunnel has always been there and cannot be built, modified, or entered from the outside. Mathematically valid, physically unreachable. And then there is the issue of acceleration. The transition from subluminal to superluminal is not smooth. As a warp bubble approaches light speed, the geometry changes qualitatively, horizons form, causal separation emerges. The interior becomes isolated from the exterior in profound ways. This transition is not like increasing the throttle on an engine. It is more like crossing a phase boundary, ice turning to water. The physics on one side does not simply extend into the other. And when physicists analyze these transitions carefully, they find that energy requirements spike sharply at the threshold. Even configurations that use only positive energy below light speed tend to reintroduce exotic requirements when crossing into superluminal territory. The wall reappears, just in a different form. There are also attempts to exploit the nonlinear nature of Einstein's equations. General relativity is not a simple linear theory. Gravitational fields interact with themselves. Energy curves space-time, and curved space-time influences energy. This complexity creates room for clever arrangements. Perhaps multiple positive energy distortions, arranged precisely, could collectively mimic the effect that negative energy would otherwise produce. But detailed studies consistently encounter focusing theorems, deep results within general relativity that constrain how positive energy affects space-time. Positive energy focuses geodesics. It pulls trajectories inward. It strengthens convergence. The warp bubble, in contrast, requires defocusing in key regions, space-time spreading outward rather than inward. And focusing theorems are not superficial rules. They are consequences of the core structure of the equations. Trying to force positive energy to behave like negative energy is like trying to make gravity repel without changing gravity itself. The geometry resists. Then there are proposals involving modified gravity, slight alterations to Einstein's equations, inspired by attempts to explain dark energy or cosmic acceleration. In some of these alternative frameworks, warp-like solutions appear easier to construct. But there is a price. General relativity has passed every experimental test put to it, from the precession of Mercury's orbit to the detection of gravitational waves. Any modification must reproduce all of these successes with extreme precision. Most modifications that permit easier warp geometries also predict small deviations elsewhere, deviations that have not been observed. The more carefully you align a modified theory with experimental data, the more closely it resembles standard general relativity. And the closer it resembles general relativity, the less advantage it offers for warp drives. Again, the loophole narrows. Another line of research examines soliton-like solutions, stable, self-sustaining wave structures in space-time that propagate without dissipating. In other areas of physics, solitons behave like particles made of waves. They maintain their shape as they travel. If space-time could host a soliton-like distortion carrying a flat interior, perhaps that structure could serve as a warp bubble without requiring exotic matter. Mathematically, some of these solutions are stable against small perturbations. They propagate cleanly through the equations, but they share the same limitation as constant velocity bubbles. They cannot be generated from ordinary space-time using physically realistic processes. They are allowed by the equations as eternal features, not as engineered vehicles. Even more troubling is the stability issue. Warp geometries, especially superluminal ones, tend to be unstable under quantum fluctuations. Tiny disturbances at the bubble boundary can grow rapidly. Radiation may accumulate. Imagine balancing a pencil perfectly upright on its tip. In principle, the equations allow it. The forces balance. In practice, the smallest vibration topples it instantly. Warp bubbles resemble that pencil, balanced delicately atop extreme curvature. Maintaining stability may require precision beyond what quantum mechanics even permits. There is also the deeper phenomenon known as chronology protection, a conjecture proposed by Stephen Hawking. The idea suggests that the laws of physics prevent the formation of closed, time-like curves, paths that would allow travel into the past. Warp bubbles capable of superluminal travel open the door to such loops. A sufficiently clever arrangement of departures and returns could create paradoxes. If chronology protection is real, then any attempt to build a superluminal warp bubble might trigger quantum instabilities that destroy it before paradox can arise. The universe would not merely forbid faster-than-light travel. It would actively destabilize any geometry that tried to enable it. Each new proposal teaches us something valuable. They reveal how tightly woven the principles of physics truly are. Energy conditions connect to stability. Stability connects to quantum fluctuations. Quantum fluctuations connect to causality. Causality connects back to the speed of light. This is not a single wall. It is a network of beams supporting the entire structure of space-time. Remove one, and the rest shift to hold the limit in place. The phrase, "scientists propose a new way to travel faster than light," is not false. Mathematically, they have. The proposals are real. The equations are valid. The creativity is genuine. But each new design does not dismantle the barrier. It reveals how deeply the barrier is embedded in the architecture of reality. The speed limit is not enforced by a single law. It is enforced by the consistency of everything. After decades of equations, refinements, and bold theoretical proposals, we arrive at a strange conclusion. Faster-than-light travel is not forbidden by a single sentence in physics. It is permitted in mathematics. And yet, every attempt to turn that mathematical permission into physical reality encounters deeper resistance. This pattern is the real discovery. When physicists first explored warp geometries, it felt like uncovering a hidden doorway in Einstein's work. The equations did not scream impossible. They quietly allowed it. The geometry was elegant. The solution was exact. But the moment that geometry was translated into physical requirements, the universe responded. Negative energy is required, but quantum theory limits it. Positive energy alternatives exist, but they cannot be created or controlled. Stable configurations appear, but quantum fluctuations threaten to tear them apart. Causality remains intact locally, but global paradoxes emerge. It is not that one obstacle blocks the way, it is that the obstacles interlock. This is not how a temporary engineering challenge behaves. This is how a structural limit behaves. Imagine trying to remove a single supporting pillar from a vast cathedral. You chip away at one stone, only to find that the arch above depends on it. Remove it entirely, and walls crack. The structure fails, not because of any single flaw, but because every piece depends on every other. The speed of light appears to be such a pillar. It connects to causality, the ordering of events. It connects to energy conditions, how matter shapes space-time. It connects to quantum stability, how vacuum fluctuations behave in extreme curvature. It connects to the very definition of distance and time. To remove it is not to loosen a rule. It is to unravel a network. And this reveals something profound about the architecture of reality. Physics is not a collection of independent laws stacked loosely together. It is a tightly woven tapestry. Pull one thread, and tension redistributes across the whole fabric. The warp drive proposals have acted like stress tests, probing the deepest structure of space-time by asking what happens if we push here. And the response is always the same: resistance. Not arbitrary, but principled. There is a philosophical lesson here. For centuries, mathematics has often raced ahead of experiment. The equations describing electromagnetism predicted radio waves before they were detected. Quantum theory predicted antimatter before it was observed. In those cases, mathematical possibility preceded physical discovery. Warp drive geometry tempts us to believe we are witnessing another such moment, that today's exotic solution will become tomorrow's engineering breakthrough. But the difference is subtle and important. In those earlier cases, the mathematics did not clash with deeper principles. It revealed phenomena that fit seamlessly within the structure of physics. Warp drives, by contrast, appear to strain against multiple foundational principles simultaneously. They challenge energy conditions, they challenge stability, they challenge quantum consistency. And every time physicists ease one tension, another tightens. The universe seems to guard its speed limit, not with a single lock, but with a system of locks. This does not make the exploration meaningless. Quite the opposite. By trying to break the limit, physicists have uncovered how deeply it is rooted. They have exposed connections between relativity and quantum theory that might otherwise have remained hidden. They have clarified why causality is not merely a convenient assumption, but a structural necessity. In other words, the impossibility teaches us as much as a possibility would. There is also something humbling in this story. Human history is filled with barriers that eventually fell. We crossed oceans once thought impossible. We flew through skies once believed sacred. We split atoms. We walked on the moon. It is tempting to assume that every limit is temporary. But the speed of light may not be a challenge awaiting better technology. It may be a reflection of what the universe simply is. A universe where causality flows in one direction. A universe where space-time geometry obeys strict energy relationships. A universe where stability is preserved by constraints that protect its coherence. And perhaps that coherence is precisely what allows complexity, stars, planets, chemistry, life, to exist at all. If space-time were easily reshaped, if causal order were flexible, if energy conditions could be casually violated, the universe might not be a stable stage for existence. The same rigidity that frustrates our interstellar ambitions may be the rigidity that allows atoms to form and galaxies to endure. From this perspective, the cosmic speed limit is not a prison wall. It is part of the framework that makes reality possible. We are not confined by a cruel rule. We are supported by a consistent structure, and yet the wonder does not disappear. The fact that Einstein's equations even allow warped geometries is astonishing. The mathematics hints at possibilities far beyond everyday intuition. The universe is more flexible, more dynamic, more subtle than classical physics ever imagined. But flexibility does not mean lawlessness. The river of space-time can bend and curve. It can ripple and expand, but its current, the propagation of causality at light speed, remains constant. Perhaps the deeper insight is this: the universe permits imagination. It permits exploration in theory. It permits us to stretch equations to their very limits. But it does not promise that every mathematical door opens into physical reality. Some doors reveal corridors of understanding rather than corridors of travel. Warp drive research has not brought us closer to the stars in the way science fiction once promised. But it has brought us closer to understanding why the stars remain distant. And that understanding is not defeat. It is clarity. The speed of light still stands, not as a challenge waiting to be overcome, but as a cornerstone of a universe whose structure is deeper and more interconnected than we ever imagined. For more than a century, physics has held firm on one idea: nothing moves faster than light.